So now we're going to do a little bit more about grammars and more general grammars than just the regular grammars we've been working with so far. And in doing so, we're going to take a peek into languages that are not regular. So before we do that, let's just remind ourselves what regular grammars are, right? So regular grammars have these kinds of rules, these kinds of production rules, right? Either we have a non-terminal going to lambda, or we have a non-terminal going to a string of terminals, a non-terminal going to another non-terminal, or a non-terminal going to this mixed up thing which has a whole bunch of terminals and then one non-terminal at the end, right? Or to summarize, we only ever have one non-terminal on the right-hand side, and if there are any terminals in there, the non-terminal has to be on the rightmost place, right? The far right of the right-hand side. So now let's talk about another kind of grammar. We touched on these just a little bit at the beginning of the first lecture on grammars, which are called context-free grammars. And you may remember that phrase. You may have seen that when you're using JFlap, right? It sometimes talks about some grammars that are context-free. So here's our definition of a regular grammar, which is pretty complicated. There's all sorts of rules. Here's the definition of a context-free grammar. The only thing you need for a context-free grammar that kind of makes it special is on the left-hand side, you have one non-terminal. On the right-hand side, you can have as many terminals, non-terminals, mixed up, anything, whatever you want here. There's none of these strict rules anymore. So context-free grammars, in some sense, are much, much easier. But in another sense, they're going to make things harder because we can represent much more complicated languages than just regular languages using context-free grammars, and sometimes coming up with those grammars can be tricky. So a very important point to note here, every grammar that's regular is also a context-free grammar, right? So if in JFlap, for example, you've seen it say that it's a regular grammar, it'll always say regular and context-free, right? But there are some grammars that are context-free but are not regular grammars, right? So as I said before, we're getting beyond regular languages, right? There's some stuff that is not just regular here. Yep, so like the slide says, get ready, we're taking a peek beyond regular languages. Okay, couple things to note before we do leave the world of regular languages. The first thing is that we're going to skip the section in the book that teaches you how to turn an NFA into a DFA. You need to know that it can be done, but I'm not going to show you how to turn an NFA into a DFA. Though it is sort of cool, please read it. It's cool, it's in the book, but you don't need to know how to do it for this class. Okay. The other thing we're going to do is we're going to skip a section on minimum state DFAs, okay? And what you need to know about that is if you have a regular expression, a regular language, there is some minimum number of states that you need to represent that with a DFA, right? And there's only one way to turn it into that minimum number of state DFA, as long as you don't care about sort of the layout of the states, is state 1 up here or state 1 down in the corner, right? You can rearrange the states physically, right? But, and you can give them different names, but there's some smallest number of states for a given DFA. Okay, so let me just give you a little bit of a picture of where we're going from here in terms of the next few lectures. In this lecture, I'm going to teach you some stuff about grammars that the textbook actually wanted you to know before you even learned about regular languages, regular expressions, etc. That's way back in chapter 3. And then after we've done that, we are going to have some practice in just figuring out a bunch of grammars. Some will be regular, some will not be regular. And then finally, to finish up our coverage of grammars, what we're going to do is we're going to talk about how can you combine different grammars so that you can, say, take the union of the two languages represented by a pair of grammars, or concatenate two languages, and how do you quickly get the grammar for that concatenated language. And the big catch here is that when you're done, you may not end up with a regular grammar. You certainly, if you're starting with context-free grammars, you'll end up with a context-free grammar. If you're starting with regular grammars, you may still end up with a context-free grammar. So here's what we're doing right now. Here's the next lecture is the practice using your wits, and then we'll do the last lecture is the wrap-up. Sorry, for a given regular language that corresponds to a DFA with a smallest number of states. So here's where we're going to go in this lecture. We're going to start, and I'm going to teach you some material about grammars that the book thinks you got way before you learned about regular languages, but I decided that you didn't really need to know that in order to understand regular grammar, so we're just going into this material in a little bit more detail now. Then we are going to learn some tricks that you can use to combine different context-free grammars, and those tricks don't work for regular grammar, so we haven't used them up till now. And we're going to wrap up with an example of how to figure out a super tricky context-free grammar, because it turns out that they're not really that bad if you just get an idea of how to sort of split it up and take a look at it. So let's go back to the material about grammars in general. So this covers regular grammars and also other kinds of grammars like context-free grammars. So here are a few definitions. Let's start with sentential form. And let's just look at this example string. A lambda capital B, right? And that has some terminals in it and some non-terminals. So, you know, that's a sentential form. And you know, A lambda little b lambda is also sentential form, but you don't have to have non-terminals or terminals for that matter in your string to make it a sentential form. Also, as we did in the first set of slides, I've been using this double arrow notation to represent these derivations, and that just says here's how you do one step. If it is the case that gamma produces this delta, then we can take the gamma in here, replace it with the delta, and call that a derivation. More just detailed notation. The double arrow by itself means derives in one step, exactly one step. If you stick a plus on it, that means derives in one or more steps. And if you stick a star on it, that means derives in 0 or more steps. This shouldn't be too surprising. So just to make sure you're clear on this, let's do these questions from the bottom up. So can you get in exactly one step from S to AAB? And the answer is, of course, no. Can we get from S to AAB in more than one step? Well, sure we can, because I think we did it before, but let's just do it real quick. S goes in one step to AB. We can replace that capital A with a little a, big A. And we can replace that next capital A with another little a, big A. So that'll take us to, little a, and then we replace the capital A with a little a, big A, and there's our B. While we'll replace the capital A with a lambda, so that goes to AA lambda B, which goes to A lambda little b, big B, goes to AA lambda little b, lambda, oops, that's supposed to be a lambda, right? And that is the same as little a b. So we can definitely derive little a b from S. We can do it in 1 or more steps, and we can actually do it in 0 or more steps. It happens to be more, but 0 or more is more. Okay. Now, I showed you one way to derive AAB, but there are, in fact, other ways you can derive AAB. So, for example, here are 2 different derivations for AAB. And you can see that they both start out the same, right? We start out with the same first step. But then we, in this first one, we're kind of doing what I did in my example and expanding the A first. And in the second one, we happen to be expanding the B first. As of right now, nothing wrong with doing it either way. It's important to note that there's not necessarily a single derivation for a given string. What we will say, however, is that you can have a derivation that you call a leftmost derivation. And when you're talking about a leftmost derivation, that's a derivation where you always replace the leftmost non-terminal first. So that's what I was doing when I was saying let's replace the capital A first, because the capital A was the leftmost non-terminal in our terminal list, right? But strictly speaking, formally a leftmost derivation is a derivation that at each step the leftmost non-terminal of the sentential form is reduced by some production. And of course, we can also say, there's another term which is called the rightmost derivation, and you won't be shocked to hear that a rightmost derivation is the same thing in which we reduce the rightmost non-terminal first. So, of course, we've talked about the language, remember a language set of strings, right? The language represented by a regular expression. So, for example, we've talked about the language of A star is this set, right? Because there's our set of strings. We can also, of course, talk about the language represented by a grammar. So if we have this particular set of production rules, right? That also produces the same language, right? That's also the language of all strings that are made up of 0 or more A's. And formally, what is the language of a grammar? Well, the language of a grammar is just, right, so here's our language of a grammar, is just the set of all strings X such that X is in capital T star. What was T? T was our terminal. So this just says X is a string of terminals, and it's possible to get from our start symbol to X in 1 or more steps, right? So it just says the language of a grammar is all the strings that grammar can produce. It's exactly what you would think the definition of the language of a grammar would be. Now we know all finite languages are regular, and it can be super simple to come up with a grammar for a finite language. So a grammar for this particular language here could be as simple as S goes to A, and S goes to B, and S goes to C, and S goes to A, B, C, right? So there's a grammar for L. Another way to write this in shorthand would be S goes to A, or B, or C, or A, B, C. But I hope that you see that if you have a finite language, it's trivial to write a grammar for it, right? Even if it's a finite language with 100 different strings in the language, you could just have 100 of these production rules if you wanted to. Of course, it's trickier when you get to an infinite language. There's a theorem that says if a language is infinite, then some production or sequence of productions must be used repeatedly to construct the derivations, right? What does that mean? If your language is infinite, there has to be some loop in your production rules, right? And so, and that loop might be a direct route where S S single arrow goes to AS, right? Or it could be something a little bit more complicated, like S goes to AB and B goes to BBS, right? So you have to keep, you know, they're interdependent. You probably heard about the pigeonhole principle in discrete math. And the pigeonhole principle, just as kind of some background, the pigeonhole principle, the short story for the pigeonhole principle is if you have 10 pigeons and 9 holes, some hole has to have at least 2 pigeons, right? If you look at our picture here, there are actually 2 pigeons. I found this on the web. I didn't cite where I found it, which is pretty bad, sorry. But it's a cute picture. But pigeonholes really, if you go to the UK, for example, instead of saying, put something in my mailbox, in the computer science department, they'll say, put it in my pigeonhole. And these kinds of mailboxes that you find in most academic departments where you can throw papers into individuals, what we would call in the States a mailbox. In the UK, they call them a pigeonhole. So it doesn't matter which. The whole idea of the pigeonhole principle is if you have, say, 27 pigeonholes, but you have 28 pieces of paper, there's going to be at least one pigeonhole that has 2 pieces of paper in it, right? If you have 9 holes, 10 pigeons, somebody's going to get 2 pigeons. And that's really, as long as you keep that in the back of your head whenever you're thinking about pigeonhole principle, it's easy. So let me give you a high-level overview of this theorem, right? So if a language is infinite, then some production or sequence of productions must be used repeatedly to construct the derivations, okay? So here is a somewhat loose but reasonable version of this proof. I'm not going to ask you to do proofs like this, but just to give you a feel, okay? If we assume the language is infinite, then there's no bound on the length of strings in the language. Strings can be as long as we want, right? Arbitrarily long. But that means if a string can be arbitrarily long, then there cannot be a bound on the number of derivation steps that we need to take in order to derive that string, right? But we said that we have a finite number of production rules. That was way back a few slides ago where we said, you know, a grammar has a finite number of production rules. Let's call however many production rules we have n. If you pick a derivation that uses n plus 1 steps, right, then by the pigeonhole principle, we're using n plus 1 steps, but we only have n production rules. We must use some rule at least twice. QED. Okay, so here's a problem from the textbook. It says, given the following grammar, looks like we have 2 non-terminals here. We have an S and D. And our terminals look like they come from the digits 0 through 9. Find a rightmost derivation of the string 7801. So one thing I'm pretty sure I said in the first lecture, but just to make sure you've got it, is that we're typically going to use S as our start symbol. You don't have to, but the book does. It's convenient. And the other thing that we are going to do is whenever we write a grammar, we're always going to write the start symbol in the first, as the first rule, right, in the top left position. So if for some reason S weren't our start symbol, the start symbol would be whatever the non-terminal is on the left-hand side of the first rule. Okay. And it looks like that we need to, if you just kind of inspect this grammar, right, if you use your wits and look at this grammar, right, what are our choices for S? S can go to a single digit, right? This is kind of the last step, whatever we do. Or it can go to a digit followed by S, right? And since we want 4 digits in our number, it looks like we need to do something like S. Our first step is going to be S goes to DS. And now, because we're trying to do a rightmost derivation, we need to expand the rightmost non-terminal first. So that means that we're going to have it go to d followed by ds. And we'll repeat this a couple more times. We'll take those dd's and we'll expand that s to a ds, right? So again, I'm expanding this s, the rightmost non-terminal, into ds. And we'll expand that into d, d, d. And this last time, I'm going to turn this s just into a d, right? And then again, we're doing a rightmost derivation, so now we need to expand this d here on the right. So that's going to go to d, d, d1. And now we'll expand the rightmost d again. So that'll go to d, d, o1. And sorry, non-traditional notation, but I'm running out of space. That will go to D801, which goes to 7801, and we're done. Okay, here's a problem from the book that is equally easy. It's just a little bit painful. So we have this grammar, right, which is a grammar of braces, it looks like, right? Square braces, square brackets, you might want to call them, right? And S can either go to a lambda or S followed by square brackets with an S inside. And it says, for each of the following strings, construct a leftmost derivation, a rightmost derivation, and a parse tree. Okay, so let's do this first one first. So I want to do, let's do a leftmost derivation for this. All right, so leftmost derivation. Well, we've got S. Don't have much choice for the first step, right? That goes like that. And then the first thing we need to do is expand the leftmost non-terminal, which is this guy. And since we have nested square brackets here, that guy is just going to go to lambda. Right? And now we expand the leftmost non-terminal, which is the S in there, so that will go to, let's see, we have lambda bracket, and then we're going to have S bracket S, like that, right? Because what we've done is we've taken that S in there and expanded it into that piece. That looks right. Okay, and now we're doing a leftmost derivation, and I think if I just replace everything with lambda, we're good. I just need to make sure I do it in the right order since we're doing a leftmost derivation. So that goes to lambda bracket. We'll replace that S with a lambda bracket S bracket bracket, which goes to lambda bracket, lambda bracket, lambda bracket bracket. So there's our leftmost derivation. I'm going to leave the rightmost derivation of this one to you, but let's do a parse tree for this. So let's see if I can shrink this up a little bit, or maybe just move it up. Hang on. All right, we're going to lose the thing at the top, I think, but there we go. Let's put that. Let's see, maybe if I shrink it a wee bit. There we go. That's not bad. Okay, so let's just do a parse tree for this derivation we just did. And our parse tree, we get the S at the top, right? And what I'm going to do for this parse tree is I'm just going to step through each step here. So kind of got, oops, I've got that one done. Now let's do this one. So the S goes to S bracket S bracket. And you'll see, just like with our English language parse tree that we did at the very beginning, the terminals end up as leaves on the tree, and we have to expand the non-terminals. So the next thing that we expanded in here was the S inside the bracket, right? And we were doing a leftmost derivation, so next we expanded this leftmost s into the lambda, and then we expanded this s into the s bracket, right? So we are up here now. If you just look at the leaves of the tree so far, that shows us what's in our sentential form, right? Again, we are going to expand the leftmost non-terminal. We're here. We expanded this one. We're expanding this one. So that goes to lambda, and then we do the next one, and that goes to lambda. So there you go. That is the leftmost derivation and the parse tree for that. Now what I'm going to do is why don't we just do the rightmost derivation for this second one, because it's pretty messy, and then I'll leave it to you to do the leftmost derivation for that and the parse tree for that. So let me clean up my screen. Hang on. And now we are going to try and do a rightmost derivation for it. It's open, open, close, open, open, close, close, close. Let's just see, did I get that right? Hang on. That's two opens and a close, so these guys are together, and we have these outer ones match up, and then we have a pair of nested ones there. Yep, that looks good. Okay, let's try a rightmost derivation for this. Right? We don't have any choice for our first step. We start with s goes to s bracket, s bracket. And then if we just kind of look at this, we can't put any more outer brackets in there, right? So these two brackets here represent these two brackets here. And this guy's going to go to a lambda eventually, except that we are doing a rightmost derivation. So maybe what I'm going to do, I'm just going to color code these a little bit. And I'm going to put a little red dot there, a little red dot there, and I'll put a little red dot there and a little red dot there, just to remind me what we're doing. So we have to do a rightmost expansion anyway. So, and we do want some more brackets inside, so let's see what we get. So we say we're going to go to s, and that guy, like I said, that first s is going to go to a lambda, but not yet. And s bracket, bracket, oops, with an s inside, right? So these two are still that red one, and now it gets interesting, right? Because, let me get another color. This S here is going to represent this piece, and these two, I think, are going to represent this piece, right? And now let's keep going. We have to do rightmost derivation, and we need another pair of brackets in here, right in here, so this needs to get expanded once more. So that goes to s bracket, s bracket. Now I'm going to expand this s into s bracket, and then we put the final two closed brackets on. So just to color code it for our own use, right? The color code is not part of this. Those are the red outer brackets, and then inside we have the green brackets, and now we'll add a couple more brackets. We'll make these ones purple. All right. And these purple ones correspond to that. But we still have not done this piece here, right? But of course we need to go from right to left. So let's just look for a minute. We have bracket, bracket. So we have the triple kind of bracket thing, right? And then we have the two out. So this one's going away, right? And then this one needs to expand to another set of brackets. So we can't expand this one to another set of brackets yet, but eventually, let's say that's going to be the orange brackets, and let's make that orange instead of green. Okay. So again, we're doing a rightmost derivation. So we need to expand this s. So we will expand that one just into a lambda now, because that's kind of done. So that's going to go to, actually, let's go to the next line. Start writing smaller. It's going to go to s bracket, s bracket, s bracket, lambda, bracket, bracket, bracket. Great. And now we need to expand, do rightmost expansion again. This one corresponds to that one, which is just another lambda. So that goes to bracket s bracket lambda, 1, 2, 3. All right. Now we are up to what I think is our orange one, right? So that needs to expand again into another set of brackets before we get rid of it. So we have bracket, and we're going to expand that orange into s bracket, and then we copy everything else that we have, bracket, lambda, bracket, lambda, 1, 2, 3. I am completely running out of space. Hang on, let me see if I can shrink this slightly. I think as I shrink this, I'm going to end up messing up some of these lines up at the top, but bear with me. Let's see what happens. Yeah. So ignore the lines way up at the top. Okay. And let's see. So, and I'll try and write more small. So we're doing rightmost derivation. So now we need to reduce that one. Well, so we will do bracket s bracket lambda bracket, and then we've got the bracket lambda 1, 2, 3, and rightmost derivation. We only have one non-terminal left, so we go to bracket lambda bracket lambda bracket lambda 1, 2, 3. And I'm really hoping that when I get rid of the lambdas, I have, I'll just write an equal sign there, right? 1, 2, 1, 1, 2, 1, 2, 3. Hurrah, I think we did it. And again, you could do a parse tree for this, right? It would start out by saying, let's just look at the first couple steps. We had our s, and that went to s bracket, and then we would expand this one and so on. This one, right? I'm not going to do that parse tree. You can do that as an exercise. Of course, we said that if you have an infinite language, you have to have a some sort of way to derive the longer strings. That comes from recursive productions. We say a production is recursive if the left side appears on its right side. So for example, here we have s goes to as. We can also say it's indirectly recursive if there's a couple of steps that get us back to where we were. So here we have s goes to little a, but big A goes to bs. So eventually we get back to that s. Whoops, and I think I gave away my answer to this question here. A grammar is recursive if it contains at least one production that is recursive or indirectly recursive productions. So are all grammars for infinite languages recursive? Yes, of course they are.